Hi, thanks for joining me on this session on the MLOps Roadmap. I want to start by actually asking the question, what is MLOps? Because it's clear from the work we've been doing to date there is a lot of confusion about what that means and what the methodology really encompasses. So for many people, MLOps is focused on the idea of taking machine learning assets and putting them into production environments. But we would argue that actually the real challenge is in allowing people to manage machine learning assets as part of a wider product or solution, which is the thing that they really care about in terms of controlling the life cycle and the release process. So for us, we define MLOps as the extension of the DevOps methodology to include machine learning assets as first-class citizens. So fundamentally, machine learning is part of your product. It is one tool in the toolbox that allows you to take your product to market. So what's the problem that we're facing in this space? Well, clearly right now the majority, around 80% of machine learning based projects are failing to make it successfully into production environments. So we clearly have a significant problem with our ability in general to convert our machine learning experiments into practical products. Now, we are also operating in an intrinsically high-risk environment. So machine learning and AI is almost always working with large aggregated data sets of potentially sensitive data. So we are always having to contend with scenarios where the challenges of the data involved are significant and the penalties for failure are potentially very high. And in fact, it's clear that we need to anticipate very high levels of regulation being introduced into this environment. We expect that in the future there will be significant amounts of localized regulation in different territories covering the use of machine learning algorithms and techniques. But there's a much more fundamental problem, which is that we train data scientists in the practices of machine learning by using convenience methods like Jupyter notebooks, for example. So we make it very easy for people to experiment and focus on the core details of building and training models. But in making that part of the problem efficient and easy to do, we're actually neglecting a large part of the technical challenges that we need to then take those models and put them into production environments. So if you step back and take the bigger view, it's clear that Jupyter notebooks are not production-ready assets. They're very easy to write and modify off the cuff, but they're also very difficult to manage effectively, put good governance process around, and extremely challenging to scale and secure, and all of the other non-functional aspects that we need to manage when we're dealing with technology in production environments. So the roadmap came about as an attempt to try and capture in one place all of the requirements for what MLOps and MLOps tooling needs to be able to do in the future to get us past this phase where we're still in the early infancy of a new discipline, and to move us into a situation where we can actually work efficiently and safely with these types of assets. So the roadmap itself is a collaborative document that we publish on an annual basis, and what that document seeks to do is collate all of the known challenges that exist in this space and capture them in one place so that everyone can have a shared understanding of what the full picture of the challenges are in the space, and we can help to communicate what the primary issues are, what we see as being the most difficult challenges at that moment in time, and help to encourage vendors and providers of MLOps platform and tooling to work towards shared goals to actually deal with the challenges that we face. So the document has three primary sections: the challenges chapter, which takes us through each individual fundamental problem or issue in the machine learning space, and tries to spell out what those challenges look like in terms of the impact that they have on a team or an organization. Then the second primary chapter is the technology requirements section. So that reflects each of the individual challenges that we've identified, and then tries to spell out some of the implications on the technology or the software that we need to solve those problems. Note that we're trying to keep the requirements as generic as possible and to not solutionize during this stage. And then thirdly, we look at potential solutions and the timeline in which we expect things to mature, looking forwards over the next 5 years. So, for example, a typical challenge within the roadmap would be the idea that we need to be quite platform agnostic in the way that we work. So, historically, machine learning has been very much a Python-based activity with lots and lots of tooling and libraries developed within Python. But that brings with it certain challenges. So, for example, because Python is an interpreted scripting language, it means that the source code of a Python environment is always available in a production environment, and you're effectively able to, if you have access to that production environment, modify the source code and change the behavior of the system that's running. So clearly that could be very high risk from a security perspective. It'd be very easy to inject malicious code into Python environments. So the other challenge in this space is that we are looking at a situation where you need to be able to build your code to train your systems. You need to be able to run those trainings, and then you need to take the trained models and move them into operational environments. Now, the reality is that the technology that is most convenient for writing training scripts is often different to the technology that's most efficient for running the trainings. And again, the technology which is optimal for then operating those models may be different again. So, we fully expect that customers need to be able to easily define their models so that they can build new products as quickly as possible. But they will typically need to use significant amounts of training resources to actually train those models in a timely manner, which may imply the use of, say, GPU resources in a cloud environment to give you short-term access to a large amount of compute resource. But then the model that you've trained is quite likely to be some sort of decision-making system that needs to operate in near real time in human-facing environments. So then you have the challenge that the deployment of your model needs to be able to operate in the real world, possibly on an edge device. So the inferencing that you're trying to do needs to be able to operate at very low latencies close to the source of the data that it's collecting. So, clearly a significant challenge exists in how we provide an overarching CI/CD process, if you like, which allows you to define models using one level of abstraction, train them using a different level of technology, and then translate those models so that they can be deployed into a third level of technology. So perhaps working from a notebook-like syntax to a native language more suited for rendering your model in a GPU-based environment, versus then taking that model and abstracting it so that it could be deployed, for example, in silicon on an ASIC or FPGA and put into a mobile device and shipped to large numbers of customers. So clearly this is a really big challenge, and it's not something that we're going to fix overnight, and it's not something that we can do on our own. So how do you find the roadmap, and how do you contribute to it? Well, the roadmap document itself is publicly available, and you can see it here. And there are many ways in which you can contribute to the work that we're doing. We're more than happy to accept pull requests on the document itself. So if you feel there's a challenge that's missing or a technology requirement that we should detail, then you're welcome to edit the draft version of the document, and we'll review and incorporate any feedback. You're also more than welcome to join the MLOps SIG. We have regular meetings where we discuss the progress of the roadmap, and we also have a mailing list and a Slack group where you can contribute and contact the various members of the team. So I hope this has been a useful session, and let's open things up for questions. Right, I hope that was helpful, and I'd be really interested to know who's involved in doing MLOps related activities at the moment, and who's planning to do so shortly. So feel free to let me know in the chat if you're already on this journey, and if you've got any specific questions that I can help with. So the plan really is to try and evolve this incrementally over time. You know, we've done quite a bit of work this year to put the first draft together, and you know, we hope that, you know, we've got a starter for 10 in terms of highlighting what a lot of the common problems are and some of the bigger challenges. So, you know, clearly what we really need to do here is to extend DevOps so that it takes into account the needs of machine learning and AI projects. So really the challenge here, James, is to make sure that the focus is always on reducing lead time. So what the practice is doing is setting you up to minimize the time it takes you to get from a decision about a feature to implementing that feature in a production environment. Now, that's not necessarily as simple with machine learning as it is with some types of conventional software applications. So, you know, there are some significant challenges in some areas. And clearly, one of the big differences is that when you're dealing with MLOps, you have to manage your data sets as well as managing your code base. In fact, many cases, the data sets are much larger and much more significant in impact than any code that exists within or surrounding the model. So, you know, there are some significant gaps in our current tooling and capability in terms of being able to treat a large set of data as a coherent asset that we need to manage over time. And you know, to give you a feel for that, a large data set in machine learning terms probably starts at about 10 terabytes of data, and may go up to tens of petabytes. So you know, it's not a case of being able to take a snapshot of something and just throw it around in the data center. You know, you're talking about very large amounts of data that take considerable amounts of time to even move from place to place in some circumstances. So clearly we're not there yet, and you know, I think we'll look back at this period and see it as the very early days of machine learning and doing AI in production. So, you know, clearly there are a lot of challenges where we're talking about solutions that want to use AI as part of a product. Because one of the big differences between conventional software products and AI solutions is that AI solutions are going to be fundamentally decision-making systems. So we're going to rely on them to make near human level decisions in lots of instances. And we want them to be able to do that in near real time. So they need to live functionally at the edge of the network. So they need to be on your mobile devices, they need to be in your vehicles, they need to be surrounding you in your smart cities. And in many cases, they need to operate at very low latency. So you need the system to react to what's going on and respond in milliseconds, because you may be dealing with a safety-related system like an automated braking system on a vehicle, or a network of systems that's interpreting traffic and trying to optimize the operation of a set of traffic lights. So one of the challenges for MLOps as a process is that you need to gather a large amount of training data from the edge. Then you need to move that somewhere where you can process it to actually train a reliable model. So that typically means moving a lot of data into the cloud, and then using a lot of GPU or TPU resource to build a model. But then you need to take that model and transfer it back out to the edge so it can run near the source of data at very low latency and do the inferencing where it's close to where it's most needed. So, the implication of that is that rather than building a piece of software in one ecosystem and deploying it in the cloud, what you're really talking about is having to go through multiple translation steps where you take something in one layer of technology and train a model, and then you take that basic model and you turn it into an abstraction that you can then translate into another technology layer. For example, you may well need to take your model and convert it into a hardware description language like Veracode, and then take that and use that to make a physical product, such as an FPGA, which you can then embed in another piece of technology, and so you then have a high-speed model that can inference very quickly, but is encapsulated in a piece of hardware. So it gets around the need to have a lot of non-specific processing power in order to be able to run the inferencing. But of course, the challenges there are that you're having to deal with a lot of complexity in your pipeline. So you're having to manage moving between multiple layers and having to abstract between very different domains. So what are people engaging with at the moment? What problems have people come across to date? Serverless, yeah, that's an interesting question. The challenge with machine learning at this stage is that it relies heavily on some sort of hardware acceleration. So you either need to be using GPUs or TPU cards somewhere in the process to actually accelerate the training to a reasonable speed. And so part of the challenge is if you're dealing with terabytes of data that you need to work with, you're having to break that up into small chunks so you can actually do the math on it to train a model. So an individual GPU card might have 40 gig of RAM available. So to be able to train a model in a reasonable timescale, less than a week, you typically need to have a lot of GPUs and then a very high-speed network so that you can continuously stream the data in 40 gig chunks through the network, performing a lot of calculations on it, and then synthesizing a model on the back of that. So serverless is an abstraction that we can use at one level. So from a data scientist perspective, you can say, yeah, well, this looks like it's serverless in that I don't have to think too much about the infrastructure. I just tell it what I want it to do. But under the hood, the MLOps implementations actually need to physically allocate GPU hardware to nodes, and then individual containers have to mount individual GPU instances, and we have to help to distribute the workload across those. So it's certainly a domain in which the tooling itself needs to be much more aware of the hardware and the physical constraints than with conventional CI/CD environments. What other challenges are people seeing? I know we've had some interesting problems just managing the governance processes around these sorts of issues. I think probably if anyone's got any further questions, might be best to take them to the MLOps Birds of a Feather event that's coming up next, and then we can start to get our heads together and dig into some of the detail of this stuff. But if there are no further questions here, then thanks everyone for your time and attention. And yeah, please reach out, get involved with the roadmap, and look forward to collaborating with you in the future.